All right. Hello, everyone. Welcome back to CPE 517-WS Digital and Computer System Architecture course. This is lecture 3 of instruction set architecture, and this is part 3, addressing and operators. Okay, so typically we have 4 ISA instruction set architecture design. That is the stack-based, accumulator-based, register memory-based, and register based. Let's see how it works. Assuming you want to perform A plus C and store it in C, stack-based one would push A in stack and push C in stack and add and pop C. Accumulator-based would load. So you see there's one load from the memory A to the ALU, and there's a add C. C is here still in register, and then store back to C. Right? And then register memory based would be load A from memory to register, and then add register of A, R1 is A, and C is already in register, and store it, and the result goes to R3, and then you store it back from of R3 back to C. And then register based would be load from memory to register, right? A is memory to register, and load C from memory to register, and then add these two together and then store them back to the memory. So you can see here the difference, right? The register based contains more. We're going to talk about it here. So load store based like are the register based, right? So we have which is the most popular one. We have like MIPS, Alpha, ARM, PowerPCs, Bark, and then register memory based. Sorry, register memory based is most popular. The load store based is the supported number of memory addresses are 0. So in the instruction of opcode, you can never have a memory address. Maximum number of operands allowed is 3. It's more used for embedded systems like ARM. Okay. And then register memory based, it allows one memory instead of it. The maximum number of operands are 2. The representative one are Intel's x86, AMD 8064, IBM 360, which is a server-based, and Motorola, which is already gone, I think. And then the memory-based are like VAX, which is a very old computer architecture. So let me take a look. So the detailed VAX computer VAX computer is a CISC instruction computer, which is popular in middle 70s, right? It's a Digital Equipment Corporation, DEC computer. Although this computer was manufactured long time back and it becomes very popular later, but right now it's already not supported. Okay. Okay. So what's the pros and the cons, right? For register based, it is simple fixed length instruction encoding, simple code generation model. Instruction takes similar number of cycles, clock cycle, except load and store, because the other ones are all data already in register. It should be relatively simple. But it has the cons of higher instruction count, right? And the low instruction density leads to large programs. This is going to give a big pressure for instruction caches, right? Register memory. Data can be accessed without a separate load instruction. Instruction format tends to be easy to encode and yields good density. Operands are not equivalent since a source operand might be in register or in memory. Encoding a register number and a memory address in each instruction restricts the number of registers we use. It gives a lower pressure to register, right? Clocks per instruction might vary because if it is register based, typically it's faster than register memory based because accessing memory takes time. Memory based instruction, it is the most compact, does not waste the registers for temporary informations. However, it has a large variation in instruction size. Memory access creates memory bottlenecks. It's not used today, like what I said in VAX. It is invented. Vector by DC, but later it's gone because it's people figured out this is relatively too time consuming for memory instructions. Okay. Then let's go to big ending and little ending. So I bet all of us have heard about big ending and little ending. It's relatively straightforward, I would say. So by putting the bytes whose address is at the least significant position in the double word is the little ending, right? So little ending puts the least significant data in the ending as the ending, right? Big ending means put the most significant data as the at the end. Right. For instance, we assume 0x, 0a, 0b, 0c, and 0d. The 0d is the most significant digit. Okay. If it's a little ending, we're gonna put 0a as the end, and then 0b, 0c, 0d, because the ending is the least significant. Big ending would put the most significant digit at the ending. So that's 0d and then 0c and then 0b and then 0a. Okay. Alignment. Alignment is actually a very important topic. We have to roughly, we had roughly interacted with you guys, I believe, in operating system. And then right now we go to computer architecture, should be very thoroughly discussed here. What is memory alignment? Assuming we have 8 bits as a byte and half words of 16 bits, one word has 32 bits, double words of 64 bits, to an access to an object of the size s bytes at address s is aligned if a module mod the size of s is equal to 0. If it is misaligned, that would request us to access multiple data in order to accommodate the request. This is a great explanation. Assuming we have 0 to 7, 8 bytes. If we do single byte based, then it's always aligned, no matter what you start with. for 2 bytes, you have a chance of misalignment. For instance, if you start with the address 0, byte is 0, then you don't have misalignment because it's 0, 1 is one half word, 2, 3 is another half word, etc. But if you're starting from 1 to 2, we see this is a misalignment because it requires us to first access this 0 to 1 and use the tail of the 0, 1. Right. Let me draw it out. Like this. If it's misaligned, we're going to have to access the first, then the second half word. So since you can see here, since we only need this byte, this half word, right? So what we're going to do is we will take the latter half of the first half word and the second half, the first half of the second half word, and then concatenate them together to formulate the first requested half word. So this tells us that we have to first load 2 half words and then do concatenations in order to satisfy. And you can see that misalignment actually is a chain reaction. If the first one is misaligned, the second one, third one, fourth one, all of them are going to be misaligned. This would be a big problem. So, and then there's a 4 byte. So you can have a line if you start from 0 to 3, 4 to 7. However, if you start from 1, start from 2, start from 3, you always have misalignments. And then when it goes to 8 bytes, like a double floating point or double word. So you only have one way of alignment, where other cases starting from address 1, okay, address 2, address 3, until the end of the addresses, you always have the misaligned addressing, okay? So a couple of side talks. I know this might not be happening right now, but for one thing you can keep in mind is we have page alignment, okay? So when you do memory allocation, if you use the Lec3 mem align, I wrote here, to allocate space, it would be typically faster than what you allocate from malloc or calloc because of alignment. It's like some noticeable 1%, 2% performance difference. Because operating system already been optimized to make aligned allocations, but just in case you might not have the aligned, page aligned allocation, so that would be a problem. But typically that's very rare. If you observe that, it's like 1% to 5%. If you are interested in this, let me know. Shoot me an email, okay? Operators. There are quite a bit of different operators, like arithmetic and logical operator, what we discussed in part 2, like add, multiplication, division, logical instruction like and, or, nor, XOR, etc. Data transfer instructions are like load and store. Control instruction like branch, jump, procedure, call, traps, returns. System operations are like interruptions, OS calls, virtual memory, management instructions, floating point operations like add F, multiply F, addition F, division F, right? Compare F, the floating point 1. Decimal operation like integers, string operation like string move, string compare, string search, graphics like pixel and vertex, operations, compression, decompression operations. Okay. branch instruction. Okay, so condition code use test special bits and use condition which is used in x86, ARM, PowerPC, Spark. Condition register are used by Alpha and sorry, this is MIPS. Compare and branch is used by PA risk and VAX. So condition code use how condition is tested, test special bits. Condition register tests arbitrary register with the results of a comparison. Compare and branch. Compare is part of the branch. So we see condition code is probably the most popular one because the condition set for free and CC is extra state. Condition register, it's simple because you can use any register with the results of a comparison. However, the cons is it can use up a lot of registers, right? Compare and branch, it only require one instructions. However, might be too much work per instruction for pipeline for us to do the compare and branching, right? Because compare is part of the branch. Okay. Well, however, condition code means compare is done, not part of the branch. The branch is just a special bits. You only have to test that specific bits. Okay. So this is something very interesting, right? So we might feel condition instruction is not that popular because in our code we typically didn't write if else, while loop, for loop, those kind of things. However, according to top 10 instructions for x86, we see that branch instruction takes 20%, which means every 5 instructions, will have one branch. And if you know that branch instruction could lead us to a different next instruction, so it can be evaluated as true or false, then it goes to different instructions. So that's actually very harmful for computers to execute. So that's why actually there's a lot of research in branch instruction. Okay. And then we have load instruction, which is the memory instruction. So we also have the compare. We also have the compare instruction that is very close to the condition branching. Then we have like 16% and store instruction 12%, add, and those are below 10%, right? So you might feel add is more popular than branching. Actually, branching is the most popular. It's a very popular one, I would say. Taking all of them together, the accumulated they account for 96% of the total instructions. Okay, so we say branch instruction is actually so popular here. Okay, this is one type of the branch instruction, like procedure call. Okay. So I don't know whether you guys heard about context switch. This video actually shows what is the procedure call. The situation is like this: assuming we're working on one thing, the caller, and then in the middle we call some other instructions. For instance, like I'm moving the mouse here, right? So my mouse is moving. Actually, if my mouse is here, it does not move then the CPU that the instruction that occupy this CPU is pretty much the Zoom or the PowerPoint. But once I touch the mouse, like I'm moving the mouse, every move you see here is actually one interrupt that is passed to the operating system, because the mouse is a peripheral device, right? So it always triggers the interrupt to the operating system. Okay. So there are two questions, right? What if the caller and callee use the same register for different purpose? So what we're going to do is we're going to first caller will save the register before the calling the callee, and the callee will save the register before using those registers. So this makes sure we didn't corrupt the data from the caller. Okay. For more rigorous explanation, please go to the YouTube here to say it. Data allocation, because we talk about memory here. So data allocation, the two most popular one are the stack and heap. Stack are reserved for local variables. It has a very specific limit, like here. Okay, heap are dynamic objects. If you are using new malloc, calloc, typically the data structure you go to is the heap. Global data area allocates statically declared objects, global variables, and constants. A large percentage of these objects are arrays or other aggregated data structures. Okay. Instruction encoding, this is going to be discussed in RISC-V. Okay. So basically, a specific range of bits are for a specific purpose. We're going to discuss them later. For instance, in x86, we have a specific rule of how many bits are for opcode and how many bits are for address, like address 1, address 2, and address n. This is for CISC, right? For fixed ones, like you have only one opcode, one field, 3 fields of opcode operands. The hybrid would be sometimes a different length, sometimes a specific length, right? We're going to discuss RISC-V, which is a fixed length. Fixed length encoding presents a much more interesting challenge. For instance, how to fit multiple sets of instruction types into the same number of bits? It has to be predefined. Expanding opcode scheme. The opcode has variable lengths for different instructions, a good way to maximize the instruction bits. But the problem is it wastes bits on some instructions that does not use enough instructions. Type B and type A instruction, we're going to discuss that later. Okay. If you could use 15 minutes to pull out one of your program and then analyze the ratio of branch instruction, that would be very good. For those of you who didn't have that, let me paste something here. So okay, if you cannot find any source code, please use this one, which is a random code I found online, and do the discussion and let me know if you have any feedbacks. Okay.